In this video, we are going to be studying input-output models. Our goals are to understand the basic idea of input-output models, or Leontief analysis, learn some new terminology, build our basic equations for input-output models, build a technology matrix, and solve an input-output model scenario. Wassily Leontief was an economics professor and researcher, and we are going to be studying his work, the work that he won the Nobel Prize in 1983 for developing. So if you want to learn more about it, just Google his name and you will find lots of information about the work that he did. So we first need to learn some new terminology. So an economy is a set of interrelated production and consumption activities which determine how a set of scarce resources are allocated. These resources need to be allocated in a way that meet the demands of the interrelated system. So what do we mean by sectors? Well, one thing that we can sort of think of is we have maybe we have a construction sector, we have a farming or agriculture sector, we have an education sector, and we have a medical sector. So we know that in order to have construction, we're going to need wood and other materials, and maybe some of that comes from this agriculture sector. Also, in the agriculture sector, we need to build buildings to house our hay, and so we're going to need things from the construction sector. And so if we look at all of these different sectors, they're all sort of needing and using each other's output in order to create their own output. Some examples of sectors are manufacturing, agriculture, technology, utilities, lumber, construction, education, the medical sector, and we already mentioned agriculture. Let's look at a really simple example, one where we only have two sectors in our economy, water and electricity. We know that in order to produce water, and what I mean by produce water, I mean capture it, make it safe to drink, deliver it to consumers, electricity is going to be required. And some water will probably be used in the production of this water. Also, in order to produce electricity and water will also be used. So here we have this interrelated sort of scenario. Here's a graphic that shows this. In order to produce water, some of the water that we produce gets used up in the production of water. So that's this part right here. And in order to produce water, we also use some electricity. So that's right here. And in order to produce electricity, we use some water and we use some electricity. So in order to produce any water, we use both water and electricity, and in order to produce electricity, we use both electricity and water. So this part of this that gets used up in the creation of water or electricity is called the internal demand. And then the part that we have available to sell is called the external demand. So when we look at this particular electricity, this part here, this gold part, is the external, and these two parts here, these are the internal. And if we look at water, this part here, this is the external, and these two parts here, these are the internal. Typically what will happen is we'll want to produce a certain amount of water and be able to sell it to our consumers to meet our external demand, but in order to, when we increase the amount of water produced, then we have to increase the electricity, and we have to increase the water just because we know we use up water in production of water. So we can't just increase one thing without impacting a whole bunch of other things. The production level, this is the amount that we want to produce overall. Some of that's going to go to meet the internal demand, the stuff that gets used up in production, and some of it will go to meet the external demand. So let's look at some more specific details. So suppose we know that in order to produce $1 of electricity, we use 30 cents of electricity and 10 cents of water. And in order to produce $1 of water, we use 20 cents of electricity and 40 cents of water. and we decide that we need to produce $5,000 of electricity and $2,000 of water. So what we want to know is how much of our production goes to meet the internal demand and how much goes to meet the internal demand. So if we look at electricity, we know that in order to produce electricity, we're going to need 30 cents of electricity and 20 cents of electricity for our water. So if we're producing $5,000 electricity, for each dollar we use up 30 cents here of electricity, and then for each dollar of water, and we have $2,000 of water, we use up another 20 cents of electricity. So when we calculate that, we see that we use up $1,900 of electricity. And we can do the same thing for water. If we sort of calculate how much water and electricity we're going to use up, so for each $1 of electricity we use 10 cents of water. So if I take that $5,000 and we multiply it by 10 cents, and then here for each $1 of water, and we're using $2,000 of water, we're going to use 40 cents of water. So the total that we're going to use up is $1,300 in water. These two numbers here, this $1,900 and this $1,300, these represent our internal demand. And we know that for electricity, we are producing $5,000 of electricity, and so 1,900 of that is going to be used up in our production. So if we take this 5,000 and I subtract off that 1,900, we're going to end up with $3,100 in electricity that we can use to meet our external demand. And then if we do the same thing for water, we have $700 available for our external demand in water. So our big overarching equation that we have is the amount that we produce is equal to the amount that we use up in production plus that external demand. And so we're going to use this basic equation to come up with our equation that we're going to use to solve these input-output models. Also, in the example that we were looking at previously, we were given the production level. But what is more common is we're given this external demand. We have a certain amount of external demand that we have to meet, and we have to come up with this production level. So this production level is our goal. So let's look at another version of this same scenario. This time we're given the external demand. We have an external demand of $4,500 of electricity and $1,800 of water. And what we want to know is how much do we actually need to produce in order to meet the internal demand and the external demand. So I'm going to let X be the amount of electricity produced and Y be the amount of water produced. So when we think about the internal demand for electricity, remember, just like we did before, we look at how much electricity gets used up. So for each dollar of electricity that gets used up, we use 30 cents of electricity. So this is this 0.3x is the amount of electricity used up in production of electricity. And then we also use up some electricity when we're producing water. So we take that 0.2 and we multiply by the amount we produce in water. Looking at water, we know that for each dollar of electricity, we use 10 cents of water, so that's where we get this 0.10x. And for each dollar of water, we use up 40 cents of water, and so we get 0.4y. Our external demand that we're told is $4,500 of electricity and $1,800 of water. If we use our basic equation that production equals internal demand plus external demand, we get the following two equations, one for electricity, one for water. So now we have a system of two equations and two variables, and we have methods to solve this. We could just use substitution and elimination, but when these systems of equations get to have more than two variables, the this solving process is a little bit more complicated. So we're going to use our matrices in order to solve this. So let's look how we would solve this in terms of matrices. So again, here's our equations. I'm going to let x be our variables. So this is our xy 2 by 1 matrix. This part here, this we could think of as our A matrix. If we take our A times our x, notice we're going to get 0.3x plus 0.2y, and that's exactly this part. And for this row, we're going to get 0.1x plus 0.4y. That's exactly this part. And then D is our external demand. So basically, this system of equations can be written with matrix notation as x equals ax plus d. Now, we can actually solve this matrix sort of just using algebra. So let's look at this. Now, if we had an equation just from algebra and we were trying to solve for our x here, so the thing that we're trying to solve for is this x, we would probably get the x's on one side. So I'm going to subtract this ax here, and we're going to get x minus ax equals d. Now, in algebra, if I had z minus 2z equals 5, we would combine these and get a like term. When we have a variable here instead of a number or a constant, like z minus bz equals 5, what we're going to do is we're going to factor out that z, and we factor out that z, we have 1 minus b equals 5, and then we divide. Okay, so we can do a similar thing over here. But when we factor out this X matrix, we need to think about what we have left. Over here, we have the number 1. And 1 in matrix terms is that identity matrix. So remember, the identity matrix is the matrix that when we take that identity and multiply it by any matrix, that as long as the multiplication works, we just get the original matrix back. And these matrices are always 1s along the diagonal and 0s everywhere else. So in our situation, we have a 2 by 2 matrix A, so we're going to need a 2 by 2 matrix X, or I. So I'm going to think of this as IX minus AX equals D, and I'm going to factor out that X. We have to also be careful that we are factoring it out on the right side, because matrix multiplication, we can't change the order. Remember, A times B does not equal B times A in matrix multiplication. So it's multiplied on the right here, so I'm going to factor it out on the right. So I'm going to have X over here. I'm going to have I minus A equals D. And then the last thing we need to do is just get x by itself. Over here, we could just divide both sides by the 1 minus b. So, and get 5 over 1 minus b. But we can't do that in matrices because we don't have matrix division. But what we can do is we can multiply both sides by the inverse. So what I'm going to do is I'm going to multiply both sides by the inverse of I minus a. So we're going to have I minus A inverse times D. And these two undo each other. That's just going to give me IX equals I minus A inverse times D. So our solution is just going to be Ix just equals X. So our solution is going to be I minus A inverse times D. So when we have a system like this, and this is our equation, we know that the solution is going to look like this. So we still want to be able to solve this equation using our methods with matrices, but I don't want to do this calculation by hand. We could, but I don't want to. So I'm going to use my calculator here. I'm going to go in and I'm going to input my A matrix and my D matrix. So I'm going to go in and input my A matrix, and then I'm going to go in and I'm going to enter in my D matrix. And it's a 2 by 1 matrix, and I'm going to have 4,500 and 1800. Okay, so now all I need to do is I just need to enter this into my calculator so that I can solve for my x. So notice the first character is a parentheses, and then we need the identity matrix minus A. So one option would be to actually make an identity matrix, but we can tell our calculator to make an identity matrix pretty easily. We can just tell it to make an identity matrix, and we want a 2 by 2 identity matrix. So that's how we would get that, minus our matrix A. So go back here, grab my matrix A. I'm going to do the inverse, and I'm going to multiply by my matrix D. Our solution here comes up to 7650, 4275. So what does this mean in terms of our original problem? Remember, this was our electricity and this was our water. So this tells us in order to meet our external demand of $4,500 of electricity and $1,800 of water, we need to produce $7,650 of electricity and $4,275 of water. Now, typically, when we are using or solving these input-output scenarios, we aren't given the information in the same way that I gave it to you in that first problem. We're given the information in what's called an input-output matrix, hence the input-output model name. And here, instead of being told how much gets used in producing of 1 unit of each sector, we are told how much is produced for a different number of units. So for instance, they tell us to manufacture 160, let's see, they didn't tell us what our units are. Let's say this is $1 million. If we're to produce $160 million of manufacturing, we're going to use up 42 million of manufacturing and 22 million of transportation. And in this one, in order to produce 180 million of transportation, we use up 32 million of manufacturing and 38 million of transportation. So we can think of as the rows here as how much gets used up, so that's our internal demand, and the columns is our output, so this is our production. So input, output. So in order to make those the technology matrix, we need to what's called unitize this. So we need to figure out, instead of to produce 160 million in manufacturing, we need to figure out how it's going to work if we produce 1 unit. And so all we need to do to build that matrix A is to do some selective division here. So in order to produce 160 million, we use 42 million in manufacturing. So this means to produce 1 unit instead of 160 million units, we just take 42 divided by that 160. Same thing here. We're going to do 22 divided by 160. This will figure out how much we need to produce 1 unit instead of 160 million units. In order to produce 1 million units, instead of 160 million units, all we need to do is divide by that 160. Same thing for transportation. So we're producing 180 million units. So to unitize this, we're going to take the 32 and we're going to divide by 180. And here we're going to take the 38 and divide by 180. Our columns are still the same. This is still manufacturing. This is still transportation. Our rows are still the same, manufacturing, transportation. But this is to produce $1 million worth instead of $160 million worth. So here we have our technology matrix, our input-output table, and our technology matrix. That's that technology matrix right there. And so what this means is, so again, manufacturing technology. In order to produce $1 million worth of transportation, so that means I'm looking at this transportation column, that's our output, we're going to use 0.1778 million in manufacturing, that's this row here, and 0.2111 million in transportation. And in order to produce 1 million in Manufacturing, we're going to use 0.2625 million in manufacturing and 0.1375 million in transportation. So that's how we take that technology matrix and we think about what each element means. Again, we aren't typically given that technology matrix in just explicitly. We have to develop it by unitizing the information. And so in this question, this is the type of question that we're being asked. Determine the production level required to meet an external demand of 230 million in manufacturing and 420 million in transportation. So this is just like that previous problem. We know that in order to solve this, my X is going to be my production, and I'm going to take my identity minus my A, inverse, and multiply it by my D matrix. So pause the video and give this a try. One thing I want to point out is that when you go to enter your technology matrix, you don't have to enter these values here. You can enter the division. So I could take 42 divided by 160, 32 divided by 180, and this is better than entering the decimal approximates. So running through this, I got this matrix for my production matrix. One thing that they'll often do in your homework is they will ask you to round to a certain number of significant digits. So suppose they ask us to round to 2 significant digits. So when we're counting significant digits, we don't count leading zeros, and we start from the first non-zero digit and start counting. So if we look at this particular one, so here's my first significant digit, here's my second significant digit, and they're telling me to round right here. So since the next digit is larger than 5, I'm going to round this to 460. And the second one, we have 612. The 2 is smaller than 5, and so I'm going to round that to 610. So this tells us that in order to meet that external demand, we need to produce 460 million in manufacturing and 610 million in transportation. They might also ask us to find the internal demand. If we go back to our original statement, they told us that our external demand was 230 million for manufacturing and 420 million for transportation, and we just found that our production is going to be 460 million of manufacturing, 610 million in transportation. Remember, our production equals our internal demand plus our external demand. So this external demand is that D. Our internal demand is what they're asking us. The amount that gets used up in production is your internal demand, and our production is our X. So in order to find this internal demand, all we need to do is to take that X minus that D. So if I take this 460 and subtract off that 230, that's going to be 230. And if I take the 610 and subtract off the 420, I get 190 million. So the internal demand for manufacturing is $230 million, and the internal demand for transportation is $190 million. That's it for this video. Hopefully you found it helpful.